Hello, everyone. Welcome to day 2. We have 4 talks in this session. The first one will be by Alistair Stewart on the topic that Dan Bonnet talked about yesterday. And he will talk about on Reed-Solomon proximity gap conjectures.
Hi. Thank you, all of you who woke up at 7 a.m. to get here. So what's this talk going to be about? So, if you know if you went to Dan Bonet's talk, I can skip maybe 8 slides at the beginning. Basically, people who prove things about correlated agreement tended to make conjectures. All the nice properties the Reed-Solomon codes apply. They prove it for unique decoding or Johnson bound, and then they assume it goes all the way to capacity. They conjecture this, and then people in production go and use their conjectures. It's probably not a good idea, but some of these conjectures were already basically known to be wrong for 60 years. Validity coding for which the concept has been around for 70 years. And we showed that basically similar results as hold for validity coding capacity also hold for this new concept of proximity gaps. And that many of these conjectures fail at more or less the same point as they do for validity coding. And then I will address the question of what should the conjectures be now in the light of this paper and everyone else's work. Over the last 8 months, there's been a lot. Okay, so here's the introduction. You all know what a Reed-Solomon code is. Probably the different thing is I'm deciding to make the evaluation domain a vector. And that the degree is k minus 1, and the rate is k over n, is rho. Reed-Solomon codes are the evaluation of polynomials. Is this? Don't know. The Hamming distance is f. No one else uses f. And the rate delta is f over n. So if I have 2 polynomials of degree k minus 1, then the difference is another polynomial and is either 0 or has most k minus 1 zeros. The minimum distance is m minus k plus 1 between code words, so the maximum distance from the code is m minus k. And if you're within half this, then you are close to at most 1 code word. But after that, you can easily construct an example where you're close to many. But maybe we can still do list decoding, find a list of code words, and then the question for at least this talk is just how big is the list. And I don't even need to explain why this is useful for snarks. Especially if you're not using homomorphic commitments, you're using Merkle trees, then you only sample a few points, and so you always end up not knowing exactly what's going on with the rest of the vector, and the best you can say is something about Hamming distance. This is falling off. This is falling off. Okay. Thank you. Okay, so can anyone hear me? Right, and correlated agreement was also explained very well in every single talk yesterday. But if you weren't here yesterday, if 2 or more words are far from code, then the assumption of this proximity gap is that a random linear combination is far, except maybe a few points. And if you take a random linear combination, it's probably far. like either we have a few points close to the code on the line, or all the points are. Mutual correlated agreement is even more useful. You take a random combination, and the agreement set, probably over the randomness used to take the combination, works for all points on the line. Whatever agreement set the random point agrees with the code. But this seems to have fallen off again. Let me try. Yeah, if I ever look, I just have to look this way all the time, I think is the answer. Make good eye contact. I mean, I don't even need to look that way because I've got this thing down here. Okay, now what are these conjectures that people made? So for the paper that introduced proximity gaps for correlated agreement, so basically they tend to write this thing in terms of this gap to capacity, capacity meaning the maximum distance, essentially. So in terms of R variables, this is like eta is equal to 1 minus f plus k over n, or 1 minus delta minus rho, 1 minus the error rate, and the rate of the code. And in terms of this gap, you get something, the conjectures people made were, we get something polynomial in this 1 over this gap eta, the length of the code n, and the rate of the code, and for the number of points. So this is the epsilon is the fraction of points. We have to divide by the size of the field Q. And for list decoding, similarly, people suggested something polynomial in n and eta. For mutual correlated agreement, the conjecture is more or less the same as the one for correlated agreement. Now, this list decoding one is particularly suspect because actually it's been known since about 1950-something that list decoding doesn't work with capacity for any code. I think the author, to be fair, the author of this paper seemed to have said now that this doesn't work for large fields, but the fields we use for snarks are not large enough for this effect to completely be irrelevant. So it makes sense to have some modification to this. Let me explain this list decoding thing. It's actually a very simple calculation here. If you take a sort of a word uniformly at random and ask what's the expected list size, it's just a question of counting. You know, I take the number of words in a code and I multiply by the number of words close by a given word, and I just divide by the number of words in the code, and it gets its expected list size. The number of words close to a word, this is the volume of a Hamming ball, is maybe a little complicated formula, but the biggest term is the biggest term where f points are different. Well, we have q minus 1 possible values. These can be different. And choose f different sets of f points where this could be different. So you very quickly get a formula here, which works for large q. This is approximately the same. And it's q to the n minus k minus f, which is this n times eta in terms of the gap before. Exponentially small probability, but then we have this exponentially big factor, n choose f, which could be, up to almost 2 to the n. And as a result, if n is bigger than, log the size of the field, then for some points, this is, this goes over 1 for some points, and then it gets exponentially big fast. And as I said, Peter Elias showed in like 1957. Using this, that if the expected list size is bigger than something, there must be some point with this, and therefore we are only list decodable with bigger lists. So if we're bigger than the amount where this thing blows up, which is given by this complicated function here, the Curie entropy, then the list size goes exponential. And if it's within that, then actually he showed that there exists a code with a small list size. Now, it's remained open since then as to which codes used in practice might achieve this. People have proved results for random linear codes. Then Reed-Solomon's open, actually random Reed-Solomon. I don't think anything that looks exactly like this, but we have results. But it has been an open conjecture since then that maybe this applies to Reed-Solomon. There are Reed-Solomon codes that, or every Reed-Solomon code that satisfies this. Now, this being open kind of gives an obvious that this conjecture I gave in the previous slide is wrong, but there's an obvious fix. If there could be a Reed-Solomon code that had this property, then all we'd have to do is change our definition of eta back here. If we change our definition of eta to the definition in Elias's theorem, then maybe it works. But if we don't, it definitely doesn't work. OK, so what would we do for correlated agreement? So actually, us and another paper by Diamond and Gruen independently came up with the same idea to solve this problem, which is basically, so we have a linear combination. One of our words is far from the code. If we just take the other word to be a random word, uniformly at random, then I take a random linear combination of this random word with something, I get a random word. And if the question is a random word probably close to the code, and if the random word is probably closer than this word that's far, then I can look in expectation for how many points fail, and I can show that the proximity gap fails. OK, so there was a simple formula saying that beyond this list decoding capacity, in expectation, the list size is big. If the list size is bigger than 1, we're close to the code. So the question is what we have this quantity that's big in expectation. What's the probability it's bigger than maybe large in expectation? What's the probability it's bigger than 1? And the way to attack this problem is just to basically get a concentration inequality for this and say, well, okay, the expectation's big. We're probably close to the expectation, so we're probably bigger than 1. Now, Diamond and Gruen did this for basically this idea, looking at Hamming balls. If there's one difference between our two papers, is that we did it instead in the analysis in terms of agreement sets. Well, disagreement sets are what we have in the paper, but I've written this in terms of agreement sets because actually that's probably a bit more familiar to you guys. And a bit more intuitive. I seem to skip 3 slides. OK, so instead of counting the list size, you count the number of sets of size n-f, which agree with your code, with your word, agree with some code word with your word. And again, we can ask, what's the expectation? Well, fraction of words that are in the code times the number of words that agree. OK, is that what I meant? Maybe not. Number of sets of size m-f, and the number of the pairs of words that agree on A? No, that can't be it. Anyway, you do the calculation, it comes to roughly the same. Well, here we get exactly now q to the minus, and this should have a bracket around it, n minus k minus f, times n choose f. Exactly because we take a word, we take an agreement set, this is what this quantity is, we take a word, we take an agreement set, how many other words agree with this word on this agreement set? Well, there are q to the f of them, because in these f points not in the agreement set, we can have any one of q values. That includes the word itself, of course. And that gives you this formula. But what makes this easier, so again, we have this problem, we have the expectation of something, which is the number of words. We can introduce like an indicator variable for each of these things. This expectation is bigger than 1. The question is the probability bigger than 1? And how do you do this? Well, if these things were independent, we could use Chernoff bounds. They're not. First thing to do is with this kind of thing, look at the variance. And to do that, we have to look at pairs of things. So we have two agreement sets, A and A primed. And here something really nice happens. If we have a pair of agreement sets which intersect in k points or fewer, then it turns out these two indicator variables are actually independent. So this thing we got the sum of. We have these indicator variables. They're mostly pairwise independent. When you try and do the variance, you end up with, you look at the expectation of this sum squared. You end up with lots of cross terms in these things here. Cross terms of the covariance between these things, which are mostly independent, and most of the terms disappear. And the variance ends up being small. If I have any time to explain anything, I should try and explain why these two things are independent. I think I should have something technical. And this one's easy because it's just Lagrange interpolation. And absolutely all of you, probably especially the developers, will understand that ZK is all about doing Lagrange interpolation on polynomials and doing tricks. Right? So we have two agreement sets, A and A primed. Fixed agreement sets. They have some intersection, A intersect A primed. And then I take a random word. And I'm going to interpolate, do Lagrange interpolation from this random word on the set A primed, get a polynomial PA, do the same for A primed, and the same still for this smaller set, which is the intersection. How are these things related? Well, all three of these things, they got them from Lagrange interpolation. They agree on A intersect A primed, right? They're all equal to the random word, which I should have given a name, like Y. It's Y. Oh, it is Y. And so the difference in between these things divides by the zero polynomial of A minus A primed. So I can now write this sort of extension A. It's a bigger set than A intersect A primed. I can write the Lagrange interpolated polynomial for A as probability of A intersect A prime times plus the zero polynomial of A intersect A primed, where these two things agree, times some other polynomial, whose degree is smaller than the size of the difference between these two sets. And what do these things look like for a random vector? Well, this polynomial A that multiplies the z here in this PA, multiplies the vanishing polynomial of A minus A primed, because it's degree at most A minus A prime, we can just interpolate it from the points on A minus that are in A primed and not A. I think so, yeah. We can interpolate on these things. I'm not sure. That might have been A minus A primed. Yeah. Okay. And these Y, each coordinate of this uniformly random word is independent. And this yi for I in A such A prime is independent of the values on A intersect A prime. It's independent on this Lagrange interpolating polynomial. And so whatever it is in A and A primed, this quantity, this is evaluation of A minus A prime to xi, This yi is uniformly random. The denominator is uniformly random. The numerator is uniformly random. The denominator is fixed. It's and non-zero. It's uniformly random. And you can quickly see, therefore, that if we take this vector uniformly random, we do this Lagrange interpretation, then the Lagrange interpretation on the intersection and these two polynomials A, which are used to get the Lagrange interpolation in these extensions, are in fact uniformly independent and random polynomials. They're polynomials with uniformly random and independent coefficients of particular degrees. And that means that this thing is now easy. Okay, there are two sort of regimes here. It depends whether if the intersection of A and A prime is bigger than K, then any nearby code word, well, it's a polynomial of degree K minus 1. So if we interpolate it on all the points in A intersect A prime, we get the whole word. So it must be the evaluation of this Lagrange interpolation of A intersect A prime that these two A polynomials are both 0. And you can count which of these uniformly random and independent coefficients is 0, and that gives you the probability. It's q to the minus something. When the intersection is smaller than k, and now remember that if we're sort of close to capacity, that means that m minus f, the size of A and A primed, is not too much bigger than k. So for almost all things, this intersection, almost all pairs, this intersection will be smaller than k. Now what happens is that whatever this Lagrange interpolation polynomial of A intersect A primed is, its degree is going to be smaller than k. So this sort of term in the equation here for PA, this intersect term is never going to put the degree over k, for k minus 1. It has to be because this A polynomial has a degree over something. Right, the intersection has a fixed degree. So this occurs when this degree of A minus A prime is small enough. The other one, so then the A is agreed with the code word. A prime agreeing with the code word happens when the degree of the other A polynomial is small enough. These polynomials are independent. So these two, the XA and XA prime, are independent. And you can again count the probability just by counting the things that are 0, and it ends up being q to the minus m minus f minus k. Now if you go and compute the variance, all these cross terms will disappear, and you'll just have something from the first regime. And it ends up being small. Obviously, the sum is a little tricky, so I left out that and just put the easy put with good interpolation. So to convince you all that it's elementary, right? What's the result? Okay. So basically, we have this, if we go slightly above the list decoding capacity, it turns out only to be square root of the distance, the distance between list decoding capacity and capacity. We go via out square root of that. Then what happens is that proximity gaps fail. And they fail badly. Like every single point on this line is close to the code. Epsilon is equal to 1. Yeah, I can do that because this is an affine line. And this point U1 is far from the code. But everything with U1 plus lambda with U0 plus lambda U1 can be close. So everything on my line is close, even though one of the points I combined is far. And this is a complete failure. And it gives fairly nice things in basically every range that we would use for a snark. We get something a bit more general than what Diamond and Gruen showed. I should say, their result hit ePrint 4 days before ours. We also had another result, and it came out on ePrint 2 days afterwards. It's a popular area, right? And this other result, right? So we have this thing which basically says that correlated agreement fails at the same point for similar reasons as list decoding capacity did. And you kind of think, okay, well now we took these similar conjectures for list decoding capacity and correlated agreement, and we can modify them, and they also look fairly much the same. And the question is, are these things related? So the obvious question is when this list decoding, the list size blows up, does the proximity gap also fail? And the answer to that is yes, but although it has to be said the proximity gap here doesn't fail as badly as epsilon is equal to 1 before. Now we get epsilon like 1 over 2k, 1 over k. So this result is if the list size is bigger than q over k, then the fraction of errors is going to be bigger than 1 over 2k. So when the list decoding capacity fails, the proximity gap fails somewhat. I think 1 over k probably isn't useful for snark people because everything was tight, but sometimes your k might be 10 to 20, right? 2 to 20. Might be a million points that you have in your constraints you have in your snark, and then it's not useless. But the proximity gap, so this result kind of implies this result, but not nearly as bad with this bad failure. So what do? We modified our conjecture. Okay, maybe I'm going. Did we start late? No, we didn't. So maybe I'm over time. We modified the conjecture. We just replaced the definition of eta. We replaced this delta with this HQ of delta. What does that make? I even had the thing here saying how much difference that makes. What difference it makes? It makes a difference of, well, if this x here is close to a half, it makes a difference of 1 over log 2q. Number of bits of your field size. So you have 128 it only makes a difference of 1 in 128, but if your domain is 2 to the 20, that's definitely concretely a few points. It doesn't probably affect the security of your snark very much, but it definitely means these conjectures are completely wrong. So that's what we suggested. Then the results kept coming out, and it wasn't very many weeks before someone showed this was wrong. What was the issue? It's actually very simple. So if I do this thing with an extension field, and I have a subfield, and the domain also has points in the subfield, and people do this in practice a lot, then the code on the subfield is kind of a subset of the code on the extension field. And what that means, if the list size is big for the subfield, the list size is big for the extension field, but this entropy thing this decoding capacity bound hits first. And Penzi and Sancho actually looked at that this affects the concrete security of snarks. And maybe unsurprisingly now, the correlated agreement also fails. We have a result on that. It also fails badly. That's our other result. OK, so instead of using the Curie entry, let's use the Peary entry when P is the characteristic, and put that in the bounds. Great, we did that on ePrint. Now what happened is someone else did the result. This was published 2 weeks ago. We knew about it a bit earlier. And they did something which is nasty. And the real crazy thing about this is nasty for the domain to use in practice. This is, OK. I'm going to mispronounce their name, so let me not try. In particular, they gave a failure which applies for some primes and multiplicative subgroups of order of power of 2, which is what people do in practice. But actually, their result kind of extends to like many fast Fourier transform variants that don't do this. Like we do circular FFTs, additive FFTs, like even easy FFTs, if you sort of do this. And all these things have the property that there's some polynomial rational function in the case of ECFFTs, which sort of reduce your domain down to a much smaller domain. And we use this to efficiently do stuff. But this also helps break the thing with some log gap. Yeah, I say most FFTs, there's too many FFTs to do. I think radar FFTs, I've got no clue. Anyway, final thing. let's modify the thing a bit further. Instead of HP, we'll take the minimum of P and N. There was something by naming in the previous slide which vaguely justifies this, and that's what we did in the end. Should you use this in your snark? Well, the conjecture changed twice in 8 months, so maybe securing your D5 protocol with millions in TVL, don't do that. But so what, in that case, what is this conjecture useful for? Well, it's for tracking the amount of progress we have, right, on this problem that people decide is important, worth $1 million, and giving results for people, for people doing positive results to aim at. Tracking the progress for negative results, giving something for positive people to aim at. That's why we make maximum conjectures, not so that you go and use them, even though people did. Okay. Thank you.
Do we have questions from the audience? Ariel?
If you could go back to the slide, the result of all that, it was called. Just wondering a bit.
Yeah.
I wonder just if there's is the U2 there just a typo?
That should be U1. Yeah, that's a typo. Yeah.
So when you say for all epsilon, I guess epsilon 1.
No, epsilon is equal to 1. It should be for all lambda.
Yeah, I'm saying so at least for the lambda that will give you U1.
There is no lambda. Yeah, it's an affine line, right? On the projective line, there's a point that's far, yes. But on the affine line, there's none, right? So we never get U1.
0 plus lambda U1?
Yeah, we never get U1. Because the U0 is always there, right? On the project, yeah. The
then is it really... Oh, I see. Okay, so it's a little... Because usually the U0, U1 are on the...
Yeah, if you did the projective line, epsilon is 1 minus 1 over q.
Oh, okay. It'll be 1 minus 1 over...
Oh, 1
okay.
minus 1 over q plus 1.
All right.
Yeah.
Right. It'll still... Yeah, it'll work for the linear line, for the projective. Okay.
Sure.
Okay, thank you.
Okay, then for time reasons, let's move on to the next talk. And thank the speaker again.
By the way, if anyone is presenting,